and he's going to talk about like model systems for interpretability. This is actually, I didn't put many of these papers on my on the reading list because I wasn't going to cover like toy models and their importance in interpretability, but Ekdeep has done some fantastic work on that, so we'll be adding some papers to the reading list on that. Right.
Awesome. Yeah, thank you so much for having me. This is great, full circle, coming back to my academic granddad and like giving a lecture in his class. Okay, so we're going to talk about a model systems approach to interpretability. And like, just as an outline, to begin with, I'll quickly kind of like offer a framework to start thinking about different interpretability paradigms and where this notion of model systems approach will fit in. To that end, we'll slightly talk about within the framework of levels of analysis from cognitive science that people discuss in cognitive science a lot, where standard interpretability approaches fit. And from there, we'll get into the model systems approach, which is arguably a missing piece of the puzzle. And from there, finally, I'll talk about some takeaways and conclusion. I realize I have this. OK, so to begin with, let's think for a second, what counts as an explanation? Let's say you have some complex system, say the human brain, and you want to explain some behavior that the human brain is able to exhibit. Humans, we are as a species are able to exhibit. So let's say I sample from some distribution PB, where B is the behavior, PB is a distribution, some samples, and I find that there's actually an equivalent description I can write down, some function map or any other system that I can write down, such that for pretty much all inputs that can be sampled from this distribution, the complex system and my functional description, like they essentially behave the same. And this is too underspecified, of course, right? Arguably, what you could say here is like, is GPT-5 an explanation for the brain? And in all likelihood, people would throw me out if I said that. But if you think about it for a second,
I wouldn't.
But if you think about it for a second, in fact, some of the people who started neural networks as a paradigm, this was their motivation. So for example, PDP, the book that David Rumerard and Jay McClelland, who is a prof here at Stanford, wrote, they in fact motivated neural networks as like the idea that we need systems or we need protocols which can like capture massive parallelism of computation. Rosenblatt, who came up with the first essentially neural network, the perceptron, said that like this was the first system which met the requirements of a functional explanation for the brain. So these guys might say GPT-5 is in fact an explanation for the brain. And at a high level, what I want to emphasize here is that like the notion of an explanation is kind of like a moving target. The more we can explain, the more we seek to explain. So to that end, this has been like a paradigm of questions that we've had to deal with before when we were very much interested as a field, let's say in neuroscience and cognitive science, trying to explain human behavior. And David Marr, who was at MIT back then, came up with this fascinating book, Vision, where he summarized this framework for understanding different paradigms of interpretability, or different paradigms of explaining behavior. So at a high level, there's like three paradigms that he'll talk about. The computational paradigm, where all you're saying is that like, here is my system, and I just want to capture its computation, I just want to capture its behavior. So I want to offer a description which is computationally equivalent. It engages in the same behavior. You can have explanations which are of the sort that they're algorithmic. The explanation itself is going to be a set of variables. I'm going to say how these variables relate with each other, and like eventually produce outputs that match the outputs produced by my system for the same inputs. Meanwhile, you can finally have an implementation level account where I actually kind of dig deep into the neuronal level description of the brain, the system that I'm trying to explain in this case, and say that like precisely how the algorithm itself is implemented in the brain. And this is good because like it kind of offers us a way to think about like different kinds of explanation. The boundaries are very, very fuzzy in these levels of analysis, as David Marr called it. But for the sake of like kind of creating a framework, creating a protocol for for offering us like some insights into how different paradigms of interpretability are starting to organize themselves, because these are kind of like operating very differently right now. Like, can we maybe use this as a framework to see like where different paradigms fit in? Like, is, for example, causal abstraction, which I know you guys have talked about before, is it like a computational explanation? Is it an algorithmic explanation? Is it an implementational explanation? So that's what we're going to do for a second. Just go through a quick exercise for like where standard interpretability approaches fit. And if you think about it, as we were just saying, causal abstraction, the way causal abstraction starts is that you have a hypothesis. So there's some behavior, doesn't matter what we're talking about. There's some set of inputs, some sort of shape, size, color combinations. These go into like some system. There's some variables defined over here, x1 to x4, create some hidden variables, y1, y2, lead to some output z. What I'm going to do now is I'm going to say that like if I have a neural network which is able to exhibit the behavior, as in it is for the same inputs, produces the same outputs, I am going to claim that this hypothesis, like this way that like the output is generated from the inputs, is in fact equivalent, that the neural network implements this specific functionality. And if that's the case, causal abstraction then starts to go through a series of steps to unravel how to like kind of simplify the neural network to localize precisely where the parts of the algorithm are implemented, and eventually arrives at a functional description or an implementation level description of the computational hypothesis we started off with. So in the sense, one could argue that the framework of causal abstraction, it's very top-down in nature. You're starting off from computation and arriving at implementation. Of course, the question here is, where does the hypothesis come from? Where do you actually like, for complicated behaviors, we will need like maybe complicated hypotheses, and we don't exactly know where to like easily come up with that. So causal abstraction is great, but possibly a piece of the puzzle. Similarly, another paradigm that I'm sure you guys have talked about in a fair bit of detail now is sparse order encoders. So again, let's go through this exercise: computational, algorithmic, implementational. If you think about it, sparse order encoders are a response to the notion of the linear representation hypothesis, right? It's a hypothesis, or I would argue not quite a hypothesis, but like a model of how representations encode concepts. So you have some set of directions encoded in a matrix D. There's some vector Z, which is saying like how to add up these directions to define the representation V. So in some sense, what this is saying is like I can read off concepts from the representations because they're encoded along directions. And based upon that, a bunch of people at this point, for the last 2 years especially, have been pushing on this idea, on this model of representations, the linear representation hypothesis, to come up with the paradigm of what we now call sparse order encoders, and use that to explain behaviors that our models are able to exhibit. In this case, for example, we're talking about a behavior like this. The capital of the state containing Dallas is, and the model says Austin. How does the model do that? You take the features that you extract using SAEs, and then you try to describe the behavior in terms of those features. So what you can say is that the final artifact we get is a computational graph. It's a computational explanation of the behavior. But in this sense, you could say that like this approach is highly bottom-up. We're starting off with an implementational account and arriving at a computational explanation. The challenge here is that eventually one must concede the fact that linear representation hypothesis is an assumption. We are making an active assumption about how representations encode concepts, based upon which we're defining tools, based upon which we are going to get these computational artifacts like a computational graph. But this is kind of a very simplistic assumption. Neural networks do exhibit fairly complicated behaviors. So arguably, it's worth questioning, like, what if representations of neural networks have more intricate geometry? And like in my own work, as well as others' work, you can see actually like very, very complicated geometry shows up in model representations pretty much all the time. Here in this paper over here, that we put out on arXiv only about 2 weeks ago, what you can see is like we took a dino model. We take like different rotations of a cub in a background, and the model is like constantly trying to segment out precisely the object, the background, like different like scene objects, like trees and stuff in this image. And based upon that, like if you take simply a PC of the token-wise representations in this dino model, you'll see that, in fact, like the PCA basis, if you fix the basis of the PCA based on one of these angles, like the PCA itself starts to rotate. So it actually starts to like exhibit, it has some sort of an equivariant property with respect to the rotation that happens in the input space. And each object has kind of like its own submanifold in these in this representation space. Similar results can be seen kind of all over the place. In this other paper, we show like in-context representation. We'll come back to that later on. The tree of life that some colleagues of mine at Goodfire pulled out from the EVO2, a genomics language model, representations of years of the century, and so on. And I would argue, in some sense, we could have expected this timeline of events because we've been here before. Specifically, SAEs are essentially the instantiation of sparse coding for neural networks now. But before, Bruno Olschossen and David Field at Berkeley, they did this like really fascinating and really awesome series of research on taking neural recordings and like turning them into sparse codes, basically solving this dictionary learning problem with the assumption that the features, as in the codes that you're going to pull out, the dictionary elements, they're statistically independent. So you start off with a prior assumption that these are like independent features. Based upon this, like they did make like a very precise finding about the Gabor filters, and this was like a fairly strong breakthrough in the field of computational neuroscience. However, eventually our ability to record, to produce neural recordings started to improve, and we actually found that like once you start to get into like tens of thousands of, the ability to like record tens of thousands of neurons started to emerge. We saw that like representations or neural recordings exhibit like fairly intricate geometries as well. So like here, this is at this point like fairly well-known results in computational neuroscience. For example, what we're showing is a grid attractor or like toroidal attractors pulled out from neural recordings. You have grid cells, you have these curved trajectories of a monkey which is doing a task which involves like going in loops. So again, we started off with an active assumption about like the features or like specific units of computation in the brain being like these tiny features, but then turns out like in fact the population of these features, when you start to analyze them together, there's more intricate geometry involved there. And this led to like all sorts of calls that rather than thinking about individual features, we need to like kind of grapple with the fact that features or neurons have mixed selectivity. What in neural networks we nowadays call polysemanticity, that like the same feature can activate for multiple concepts. And correspondingly, rather than thinking about, or rather than trying to interpret the brain at the level of like individual neurons, we should be trying to think about cell assemblies or populations of neurons simultaneously. And this led to like more structured dictionary learning protocols, in fact, by Bruno Olschossen's group, on trying to understand how, trying to pull out like more structured representations, like more structured geometries out of neural recordings. And in my own work, like we've been trying to pursue this paradigm as well. So over here, we take the assumption that representations are in fact points, not directions. So like the metric, as in the distance between them, like matters, like being close in the representation space matters. Similarly over here, we make the assumption that like representations encode hierarchical geometry, and based upon that, we start to like create new structured dictionary learning protocols. And over here, this is essentially like something very related to a lot of computational neuroscience work on taking RNNs, fitting them to specific tasks, and then linearizing them, and then trying to use that to explain the behavior of the task that you started off with, and how the model performs that. In this case, this is a language model now, a Gemma 2B model, and what we see is like if you take a story, like this new protocol, it like unravels the dynamics of the story into like tiny events. So like you can see there's a bunch of points floating around here, but they assemble into like tiny points, so like a set of points here, and that's because there's a precise event happening in that story, which is why like these points cluster together. So the reason I wanted to like quickly show these.
Could you say more about that last thing? So what are you actually doing there?
What I'm doing over here is I have a like a Gemma model. I'm going to take its representations at some layer. So this is like the middle of part of the model. And rather than doing making the assumption that representations are a sparse combination of concepts, we're going to make the assumption that actually the representations are in fact dense, because as you go through, for example, a story, like the concepts you're dealing with, for example, a protagonist, more and more concepts add, so like the representation can get dense as a function of that. So what we're going to say is that like even though the representation itself is dense, with respect to the context, so if I remove just this current token and look at everything in the past that happened, with respect to those representations, there's a part which I can predict about the next token representation because I can predict what's going to happen. That part is dense because that's an aggregation of the context, and everything that I cannot predict is sparse. That there's sparse changes that happen at the level of a token. Based upon that, you can kind of like instantiate a very sort of RNN-like protocol. It's not an RNN. It's actually like an attention-based protocol that we'll use. But the dense part that we are talking about, the contextual part, this is the contextual representation. And this is so like a contextual explanation. And everything that was novel, as in like we were unable to predict that for that representation, that's encoded over here. So this is very much like the standard essays. You'll find that like, in fact, like pretty much all the time I've been seeing like the inferences or the interpretation that we get from standard essays, you can pull out just from this novel part. But the dense part actually has like a lot more contextual information, like where the story is going. And if you want to steer at a high level, like the narrative of the story, this is where you want to attack. Going back real quick, we started off with like essays and trying to fit them in the levels of analysis and saying that they're a bottom-up approach. And indeed, as I was saying before, the linear representation hypothesis is an assumption about features being an additive, representations being an additive mixture of features, which implicitly is suggestive of the assumption that features are statistically independent of each other. And if representations have more intricate geometry, you'll get different protocols out. So like if you were to take that geometry to heart and create a protocol out of that, you'll be able to like explain different kinds of behaviors. Overall then, what we can think about here is that in the levels of analysis, different interpretability paradigms are following different directions from top down to bottom up. And in some sense, what we're missing right now is this middle part. There's one approach which starts off with a specific hypothesis and tries to get into the implementation. There's one approach which starts off with an implementational account and starts to get at like, how do we explain the computation? And if we had like some way to, let's say, take, put forward an approach which could offer us what are the variables that the system uses to exhibit the behaviors that it exhibits, and like how these variables come together to define the behavior, then that can be like very, very powerful. Because, for example, in regards to causal abstraction, if you have such a paradigm, it can offer the hypothesis that causal abstraction is looking for. So it can interact with causal abstraction to like look for an implementation. Meanwhile, with respect to essays, it can become kind of like a benchmark for essays. So an essay, if you have a good algorithm and good algorithmic explanation, then SAE or an implementational account has to be able to explain that algorithmic account. So this is where the main point, the main topic of the lecture will start, a model systems approach. Specifically, what I want to argue is that there was like a missing piece of this puzzle, and we can perhaps take a different approach to like starting to figure out how to fit this piece. Okay, so model systems are a fairly common approach in, again, like in neuroscience or generally natural sciences, where you have some target system which is too complex to explain by itself. So what you would do is you would define a model system. It's a system which has ideally has gone through similar adaptive pressures in the environment such that we can expect that it also, if it exhibits the same behavior as a target system, it exhibits more or less likely to be that it exhibits for the same reasons. So something like, often if you're trying to understand navigation, you could use a fruit fly as a model system for the human brain. The system ideally is simple enough that we can in fact reverse engineer it. We can try to actually poke around with it, poke around with neurons, poke around with like how it implements the behavior that it implements, based upon which we come up with predictions for the target system we started off with. So like it gives you like a precise algorithmic account, like what are the variables that mattered for this toy system, this model system, and if my target system is using similar, is trying to implement similar algorithms, even though I do not know what the implementation looks like, I can say that the variable x matters for both these systems. And if I were to intervene on that variable, both these systems will have a systematic change of behavior. So what I'm going to do now is like go through a case study of like following this protocol, following this approach. Like if we, in some sense, like this is a newish paradigm for at least neural networks research. I would not say for computational neuroscience, especially in front of Surya. But generally speaking, like if you had to do this for, let's say, neural networks, like doing a case study can like help us get some insights into like what are typical questions we need to grapple with. Okay, so we're going to talk about in-context learning and the phenomenon of many-shot jailbreaking. Specifically, in-context learning is this really cool capability that like language models around 2020 started to exhibit, where I can just like in context provide exemplars for a task and then like give a new query to my model, and the model will be able to perform that task. Personally, when I was making these slides and I was looking at this example, it took me a second to realize what's going on, because I come from India and we don't write dates this way. But this is like apparently year, month, day, and you need to sort it out as month, date, year. And you get finally this answer where the model is capable of putting the date in the right format. This is very toy, but if you actually want, models can now perform like fairly intricate and like fairly complicated tasks this way. So here, there's a language called Calamang that apparently has only about 100 to 200 speakers in the world. And if you simply put in the grammar book for this language, a dictionary, and like some translations, you can find that like if you give the model a prompt for like for translating from English to Calamang, this is in this case the Gemini 1.5 model, it was in fact able to perform that. This is not perfect. It does work, however, like fairly reasonably. And as has been the paradigm of machine learning over the last few years, whenever we see an axis which is leading to improvements, whenever we see like, let's say if I add more parameters, like if I have large models, like it gets me good capabilities. Similar things is what we're going to try over here within context learning, where people realize that like actually this is a pretty easy axis to scale. So I'm going to just like keep on adding more and more exemplars in context and see whether the performance improves. And what you find is, for translation in this specific example and from this paper, that for translating between languages, there's a fairly continuous and monotonic trend where the performance just keeps on improving. In this case, arguably, we just like lost the ability to add more exemplars, in fact. But then came this really interesting paper. I would argue actually they came around similar time. But came this really interesting paper, which was also trying to scale up the number of exemplars provided in context, but saw a very different kind of curve. So here what's happening is these are more safety relevant behaviors. So for example, you have a very well safety fine-tuned model. In this case, this was the Claude model back then. And you simply ask it to engage in violent or hateful speech, and you'll find that like it keeps on refusing it. But if you keep on adding just a bunch of exemplars of violent and hateful speech, there's some critical amount of context that you need to reach, after which the model starts to respond to violent and hateful speech, like it'll start to engage in violent and hateful speech. This is so fascinating, right? Like if I just talk bad to you, you'll start talking bad back to me. Like it's kind of like a cute and funny behavior as well. But from a point of view of safety, like this is not ideal. If I just talk bad to my models, like it's so easy to jailbreak them. Okay, so what we're going to do is we're going to like take the model systems approach, walk through like very quickly 4 papers that we worked on, trying to unravel what's going on with these with this paradigm or this phenomenon. Okay, I'm going to start off with the first 2 set of papers, lump them up into a single one. So for me, whenever I think about the model systems, I often think about neuro or cognitive literature where similar behaviors similar to language models are often observed with humans, and people have done some work on identifying or creating experiments to like unravel these behaviors or like demonstrate these behaviors with humans. So in this case, we're talking about cognitive maps, where there's this really cool experiment that was done in the group of Tim Behrens at Oxford, where they took a graph, they put like on the nodes of this graph specific objects, so like ring, ear, a motorbike, and so on. You take a random walk on this graph, and there's a human subject sitting to whom you'll show, you'll flash images one by one as a function of the random walk. So let's say umbrella, bulb, leaf, and so on. And you keep on taking fMRI recordings of their brain as they're sitting and just watching these images. Lo and behold, eventually what you find out is that if you simply do an MDS visualization, if you simply do a low-dimensional projection of the data, the fMRI data, you can in fact pull out the graph structure from the brain recordings themselves. So the subject does not know of that. If you were to inquire them, they don't actually know that. If you ask what will come after this specific image, they don't know that. But the representation exists. And what you can think about is it's not that difficult to perform this experiment with a language model. Because rather than flashing images, I can flash words. So let's just do that. What I'm going to do is I have a simple graph structure, this grid. I'm going to associate nodes to this graph, which correspond to concepts I'm very sure models have seen during pre-training, and take a random walk, feed that into create a string out of it, and feed that into a model. So this, in this case, it will be a Llama 3.1's 8B model taken off the shelf. So there's no training happening. This is entirely in context. And what you'll find is similar learning curves as the many shot jailbreaking curves that we just saw, where as a function of context, there's a critical amount of context that you reach. So these are individual rollouts, individual trajectories of different graph sizes. So we're increasing graph size as a function of color. And when you hit a critical amount of context, before that, the model, let's say if the walk ends at opera, it'll just be making random next token predictions. But after that, it starts to make next token predictions, which in fact correspond to the neighborhood of the word. So in this case, accuracy here is defined as the probability associated by the model to egg, for example, egg, plane, and mango, if the walk ends at opera, for the next token predictions, and then just observing how that accuracy changes, how that sum of probabilities changes. So it's a fairly continuous metric. And you can see as a function of the complexity of the graph, this point just keeps on moving forward and forward, which intuitively makes sense. But
So you talked about this before. So a very simple algorithm would be once you see a word, say plane, you just go back to the last time you saw plane and return something before or after it.
Yeah.
And that's a super simple algorithm. How would its performance be on that? Is it
depends.
smarter than that algorithm?
Kind of depends. It's somewhat noisy to do that because if, for example, there's an interaction or there's a transition, for example, car to plane that you did not observe in the walk, then the copying algorithm would not perform very well on predicting car to plane.
That's true.
But if you've inferred some sort of a structure that you implicitly infer, sort of a percolation process happens, and you infer that car to plane might be connected, you will start making that prediction anyway. So what happens is it depends a lot on if, for example, the walk ended up having enough coverage on the graph that it performs better versus not. So it depends on the bias of the walk.
But you can average over many runs and get an average curve and see how it compares to this or not. Does this do better than the average curve of just the random copy?
No. On average, it will not. But the variance is kind of decently high.
I see. So the variance of the average copy is not.
And that's kind of just the walk algorithm was visiting, because what happens is our periodic boundaries over here, the boundary conditions are not circular, so you reflect back. So the walk ends up traveling these middle points a lot. But where we started off, we want to get into explanations. So what we've achieved at this point is we have a toy task which reproduces the phenomenology we wanted to explain. We can capture something like a many shot jailbreaking in context learning curve, where there's a sudden bump in the learning curve. So let's see, in order to get to an explanation, let's kind of just start poking around the model a little bit. So we're going to look at the representations for a second. As I'm going through my walk, what I'm going to do is I'm going to take the representations from this, of these different concepts from the walk. So let's say the walk ends at opera. When the walk ends here, I'm going to take that representation. I'm going to find in the trajectory that just happened, find the representation of other tokens as well, and just do a 2D PCA of that. When you do this PCA, you find results that look like this. As a function of the walk, this is the PCA getting plotted for these different nodes. And what you'll see is the graph structure, in fact, is reflected in the representations themselves. So I find this personally so fascinating that model representations are extremely flexible. They, in fact, will try to adapt to the data that we're offering them in context. So in some sense, like even the notion of interpreting these models, like we need to be more dynamic with them. Like we cannot just use static protocols.
Did you run? What was this model pre-trained on? It's just a language model.
Yeah.
Which one?
Llama 8 3.1. So this is the base model.
And is there some minimum scale you need to see this structure appear in context?
So one thing that happens is, for example, like as a function of the graph size, this scales as a square root, like a power law with 0.5. And then like we tried different graph structures where the exponent keeps changing, but it depends on the graph topology.
Sorry, I meant the scale of the pre-trained.
Oh, I see. Yes, it does, but I don't want to like. Okay, I'll answer the question, but like I don't want to like lean too much into the insight itself, because like what happened is we did Llama 7B and then we went for smaller models rather than like scaling up the models. So indeed they're like more sample inefficient. They take longer. But if you were to go for a larger model, I don't exactly know if like maybe Llama 8B has already hit optimality, or like do you need more? Because this is in Markovian in nature, so you really need to like only look at a tiny bit of your context to like make a decent prediction. Okay, so we saw this fun result now, where precisely at the point where the accuracy starts to improve and the model starts to make valid predictions, you'll see that the representations reflect that. And in some sense, what was happening here is plausibly that the model first inferred the structure of the graph, and based upon the structure, then it started to, once it has that information, it starts to make next token predictions which correspond to the graph structure.
What would be like the empirical frequency of each of the words as you increase the context size? Like, would it also be that it sees more representation of the
middle
boundary, or
yeah, indeed, and you'll see actually like that's kind of getting reflected here.
Yeah.
The graph is like not a perfect square, and most of this is like an artifact of the visitation frequency. So, in fact, like a fun thing that you'll observe. I love this GIF, but like it takes so long to like always repeat it. Okay, so what you'll see is like once a graph structure has been inferred, it just keeps on expanding.
Yeah.
And what's happening is like once I've figured out the direction to encode, for example, let's say milk, every time I see milk, I just add to that direction. So the direction is fixed. Only all that I can do is I can increase in magnitude. And the tokens that like I am more likely to visit, they're like being reflected closer to the origin, so to speak, versus not. But because I'm visiting them more frequently, I am going to like have a stronger norm in some sense around them. And then like even though I capture the structure pretty well for the other like corner boundary points, it's going to be like more distorted because I don't visit them frequently.
And then how do you make sense of like as the residual stream PCA is like rotating or flipping? Like what does that correspond to?
So the PCA is getting applied every time we're like going through the walk. So like PCA does not have to like constrain itself. Like the axes can change if you apply the PCA.
So they're not the same.
Yeah, these are not the same basis.
Okay,
yeah.
okay.
If I were to do this, let's say at the last instance, then yeah, we could like unravel the dynamics themselves. Go ahead.
So you mentioned that the model do not need to see like half of the plane before like inferring structure of the graph. Really that. What if I make like a similar like framework on that, but like I cut out that edge between kind of plane? It's still a square. Still, I jump out the model like has and then how can
Yeah. So again, I love this GIF, but it'll take a second to reload it. But keep notice of the fact. Notice opera and mango. You'll see that there's no connection between them, and the graph structure has already emerged. But like actually, even when the graph structure emerged, there was no connection between them. Like the model had not yet seen that opera and mango can be connected. The walk never actually made that connection. So I'll do it again. It happens within a second, so you have to be like looking at it carefully. There's none, and the structure had already emerged, but the connection hadn't been observed. So not an experiment that was entirely in line with like, well, in some sense like randomly happens to be in line with what you were asking, but like not an intentionally designed experiment that way, where we did not like ever intentionally explore an experiment where we do not put an edge and see what happens. But if we were to do that based on this one single finding, intuition says that it might work. Yeah.
Is anything near these points that you get at the end in like token space from the unconditioned model? I guess like it's surprising that somehow there's some place where if I shift the embedding enough, it now like represents a Markov model of some arbitrary weights on the edges. Is that?
So not quite sure I follow the question, but if I to some extent, if I gather it correctly, the idea is like there's the identity of these tokens, but like so that's like the embedding I started off with, but I'm able to like shift around that embedding to like reflect this Markovian structure of the graph. And what will happen is actually like the embedding information is still available because the model eventually has to still like produce output tokens which are in this native space, so to speak, like in the token space, right? So each of these representations, like the most of the variance in this representations is explained by these two components, but there are still like more components, there's still more information available, which is encoding like these, for example, the token information, the token IDs. So yeah, like we haven't like removed that information. The prior semantics are still present. We've just augmented those semantics with something novel.
I guess like the novel semantics. Is there a semantic direction associated with like this is a Markov chain or something like that? Like,
probably not. I would argue this is a 2D subspace, so like it at the very least it has to be 2D. But like I don't think like if you want, you could say that like this 2D subspace encodes that this is a Markov chain, right? But like something, if you're looking for sort of like a pointer-like information which says like this is a Markov chain, probably not. But we'll have to do some more precise experiments to figure that out. Yeah.
And which layer of the residual stream are you doing this in?
This is layer 26. If you want, I have like backup slides showing pretty much all layers will eventually show this result. And now actually one of my lab mates has a paper like proving some of these results as well, where what you'll find is like first the representation shows up at the last layer, and then like eventually it keeps on rolling back to the previous layers. So like you'll see it at layer, let's say 28, then it shows up at 26, 24, and so on. So there's actually like a dual process happening, like as a function of the context as well as a function of the layers. So
By proof, you mean?
like mathematical proof, yeah.
Okay, let's talk about that after.
Yeah, yeah, it's actually pretty fun. So yeah. Okay, but going back to the agenda, so we see that we're able to like reproduce this phenomenon, and then like the phenomenon is very much real in the sense that the model is in fact altering its representations to like exhibit this behavior, which is sudden change in its like next token predictions. Now, what I would say is like going back to the idea of model systems, that we were able to like create a very simple toy task which exhibits the behavior we wanted to explain. So what if we now take this to heart, rather than like we first simplified the task, now let's simplify the model. So we were doing analysis with a llama model before. Now I'm going to literally train from scratch a 2-layer transformer model on a finite mixture of Markov chains, because the process that we were looking at before was just a Markovian walk on a graph structure. So here I have some state space. I have n transition matrices from which I sample a bunch of chains. And I'm going to do next token prediction to train a 2-layer transformer. And at evaluation time, what I'll do is I'll sample a new transition matrix, or I could also sample one of the transition matrices that the model saw during training. So it can be an in distribution or an outer distribution evaluation. I'll sample sequences from that and look at models next token probabilities versus the ground truth next token probabilities if the transition matrix were available to me. I can compute the KL between them, and that can essentially be deemed as my metric over here, like how accurately is my model simulating the Markov chain. Based upon this, you get a very rich phase diagram. So the model actually learns 4 different algorithms for performing this extremely simple task, where as a function of the context, an inference axis, so there's nothing to do with training for this axis, as a function of training time, the amount of training that the model goes through, and a function of the data diversity, the model is learning completely different algorithms for solving this task. So when I say algorithm here, I'm unfortunately not going to have the time to like get deep into the algorithms themselves, but what I mean is like I can literally write down in Python a file such that like the next token predictions made by my algorithm, my Python program, will be exactly the same next token predictions that my model makes at an individual trajectory, not even at a population level, at an individual input level. And another fun thing that we find is like this simple toy task, not only does it capture like the phenomenology we started off with of many-shot jailbreaking, like where as a function of context there's an algorithmic change in the behavior, you find that pretty much, to my knowledge, all the known results around in-context learning got captured in this very toy simple setting. So like it becomes a very rich and fertile ground for wanting to explain, if you want to explain in-context learning and its behavior. Okay, as a fun point, because this is technically an applied physics class, you can see there's like a nice triple point over here. It's kind of like phases coexist, like ice, solid, solid, liquid, and gas. So yeah, that was a fun thing to watch. Okay.
So now since I'm an applied physics professor,
is there like a double well potential that is variation across phase spaces, right? So this is a triple point, or is there some free energy or something?
We will get into free energy in like about 4 or 5 slides. So yes and no, I wouldn't go into like that kind of precision, but indeed, like we'll see a free energy equation explaining not the triple point, but something sort of like that. Yeah.
But more basic question: this is a theory or this is an experiment?
This is entirely experimental. So like all I've done is just like take that setting, based upon the setting, just compute the empirical KL, and I'm plotting the KL based on the KL values. I'm plotting like which algorithm is my model closest to, and it's not even actually closest. Like the KL is literally 0. So I'm simply plotting the algorithm which has 0 KL right now. And in these phase boundaries over here, in these boundaries across these different phases, what you'll find is that the model behavior is in fact like a precise interpolation between the 2 algorithms. As in, if I take one algorithm and its next token predictions, another algorithm its next token predictions, there's a precise interpolation going on between those two predictions, which corresponds to the model prediction. And we'll explain that part in a few slides. Okay, so nice phase diagrams. People love phase diagrams. So let's quickly get into kind of like recap what we did. We started off with this toy system, and what we went through is what algorithms, like what behavior the model exhibits, and like what are these axes that we need to change to like elicit these behaviors or algorithms. When that happens, so as in the function of these axes, I won't talk about it at all in these current slides, but in the paper, we talk also about how the model implements these algorithms to some extent. And we're not the first ones to do that. In fact, like a bunch of papers at Stanford, including from Surya's group, performed like similar analyses. For example, in this task that was like, I don't know, in some sense like fairly seminal work, where people started exploring toy models of in-context linear regression. I'm going to offer an input, then a label, which is like a scalar, and the model has to learn to perform in-context linear regression, map a high-dimensional vector to a scalar. And for this, as a function of the number of tasks, which in our case was the number of transition matrices seen during training, you'll see that the model transitions from one algorithm to another algorithm. Doesn't matter what the algorithms are, but they exist, and the model transitions between them. And similar behavior has been seen in other tasks as well. For example, this in-context classification task, where I offer the model let's say a vector, and it has to produce a label in some multi-class classification task. And here, as a function of training time, you'll see that like the model starts off with like a specific algorithm which is able to perform very well outer distribution, but then as a function of training time, it starts to the ability to like perform outer distribution goes away, and the model starts to behave very differently, which is in a sense like our axis over here, the function of training time. So going back, again taking a step back, what we want to do is we want to explain why the model transitions between different algorithms. Why does varying these experimental conditions, for example, context, training time, or data diversity, lead to these different strategies, algorithms for performing in context learning? So this is where the second part comes in. In the first paper, what we did now was like we want to just create like a precise algorithmic account for the phase diagrams that we were observing. So this will be basically me trying to answer Surya's question and hoping that I do not stumble. So what I'm going to do now is, if you think about it, what I was doing, what we were doing before is we're trying to like sample a bunch of transition matrices and create Markov chains out of that, and then like train my model for next token predictions. This this process can be abstracted out as like, let's say I have some data distribution, some distribution from which I sample parameters, which will be fed into some function to define one specific task that my model has to learn. So for example, in the context of Markov chains, this could be like a transition matrix. For linear regression, this could be like just a linear regression map, and so on. And then if I sample D such functions, then I get a training distribution, which is essentially a discrete version of the continuous distribution I started off with. And I'm going to train my model. I'm going to sample sequences from each of these functions and then train my model to do next token prediction. The setting I was talking about before, which was the Markov chain setting, I'm going to simplify that for a second. And we have this setting now that we're going to call balls and urns. It's kind of like the standard classical probability theory problem. I have an urn or a box which has a bunch of balls of different types in it. I'm going to sample a ball one by one and show it to you. And you have to make a prediction about what are the odds a ball of a certain type will be observed on the next round. So here we're sampling balls of different types one by one, and you have to like make a prediction about what the next ball might be. And you can easily guess like a very like an optimal way of performing this task is just count frequency. Like what is the frequency with which I observed the ball of a certain type? And we'll come back to that intuition in a second. Okay, so we have two distributions, and our models are learning different algorithms, as we saw before in trying to perform in context learning. What I'm going to do now is just at a high level ask the question that if I have two distributions, what are the optimal strategies that if my model knew that it is trying to like learn from these two distributions, what could be like optimal strategies that it tries to follow in order to produce next token predictions according to these two distributions. So fortunately, this is where Bayesian inference comes in and helps us. Let's say you have a sequence from a function, and you want to make next token predictions, which are optimal with respect to the training distribution. Bayesian inference tells us that the optimal thing to do here would be define the posterior predictive. So you assume that you have a discrete prior because there's only D functions. You compute the likelihood that each sequence has, the inputted sequence has under these functions, and then just do a Bayesian average. So just do a weighted average, prior times likelihood, sum over all the functions. I'm going to call this a memorizing predictor. It's a precise hypothesis, it's a precise predictor, which will make optimal predictions in accordance with this specific distribution. I'm calling it memorizing because you need to memorize these D functions. Otherwise, you cannot perform accurately or like optimally with respect to this distribution. Meanwhile, sorry, I kind of screwed up on that. But meanwhile, let's say if you have the true distribution, for the true distribution, the optimal thing to do would be assume that your prior is continuous. That like I have the ability to like integrate over the entire space of parameters from which the functions could have been sampled. That is almost insane to expect a neural network does that. But then we'll see fascinatingly that the neural network will do that. Okay, so in this high-level framework of a memorizing and what I'm going to now call a generalizing predictor, I call it a generalizing predictor because if you were to sample a new function, because this prior is continuous, it should be able to generalize. It should be able to make next token predictions optimally with respect to new functions as well. But the memorizing predictor can only do so with respect to the function that it has observed. And based upon that, we're going to write down closed form solutions. Fortunately, our tasks are simple enough that we can in fact write down closed form solutions for both these memorizing and generalizing predictor. Doesn't matter what they are, but we're going to use that to now reproduce the phase diagrams we were looking at before. So as a function of training time and as a function of task diversity, what we can see over here is there's a precise phase boundary where if the diversity is low, there's only a few functions that I need to learn. My model makes next token predictions which are more like the memorizing predictor. Meanwhile, if the diversity is high, then as a function of training time, or especially when the training time is low, my model makes next token predictions which are more like the generalizing predictor. What I'm reporting here is essentially the absolute distance, so like the KL between the predictions of the model versus the algorithms that I can write down in closed form. And the phase boundary over here, what you can see is like, it's essentially like it's some sort of a sublinear trend, right? So basically what this means is there's a possibility, for example, for even very high diversities, that eventually you will start to perform like a memorizing predictor. So there will be a transition that happens from a generalizing to a memorizing predictor. And we see actually this is a fairly consistent phenomenology. So like in some sense, like these are again like not new results, but just like recapping the previous results into a summary, which is this phase diagram.
The point of the transition must depend on the expressive capacity of the.
Yep.
And is this all for the same architecture?
No, different tasks have different architecture. This is a 2-layer model, this is a 1-layer model, this is a 2-layer model, and this is a 4-layer model, if I recall correctly.
They're all transformed.
But what we want to do is, as an explanation, get into the algorithm. So now, again, we've captured the phenomenology very well in a unifying framework. We can now talk about memorizing and generalizing predictors. And an important point to note here is that models are transitioning between these two optimal predictors which are optimal with respect to two distributions. This is very reminiscent in cognitive science, what we would call, or like a very evocative of what we would call rational analysis, that if your learner is behaving optimally with respect to the data, if you make the assumption that, if you want to explain its behavior, what you could do is you could make the assumption that it is trying to optimally adapt to the data under its computational constraints, which can offer you a premise or a fertile ground for writing down like a closed form expression for its behavior. So let's see what that means. This is a very high level statement. So what I'm going to do is we're going to try and now rationally analyze in context learning. We saw that the model is performing its next token predictions can be explained via two algorithms. And Bayesian inference tells us like how to optimally integrate over a hypothesis space, which in this case, if we just have two algorithms, it's just write down the simple posterior predictor. So what this is saying is, as a function of training data, SG train is a training data, what is the posterior probability of the memorizing predictor multiplied by what is the predictions that this predictor makes for some inputted sequence S, 1 to I minus 1. What is the next token probability for some observation SI or state SI, and the same thing for the generalizing predictor. So it's just like posterior weighted average. And what really matters is not this first part, is the computational constraints, because we need an expression for this probability now. The memorizing and generalizing predictor I can like write down in closed form and even implement in Python. But I need a closed form expression for these parts, the posterior probabilities now. This is where the computational constraints kick in. One of the constraints we model, for example, in this paper was scaling laws. We know that neural networks exhibit scaling laws all the time, basically, such that what you can say is that to define the posterior, there are two terms that are necessary. There's the prior and there's the likelihood. This is trying to capture the likelihood. And we're going to say that according to scaling laws, the likelihood should scale in a power law fashion, because the likelihood is essentially the loss. So it's not directly the standard form of a scaling law, because like based upon the assumption of scaling laws, you have to do some analytical derivation, which arrives at this form. Doesn't exactly matter what that is. And then the second thing is the prior. A phenomenon which has often been talked about in the literature with neural networks is that neural networks exhibit a simplicity bias, that they tend to prefer solutions which are simpler. Unclear what simplicity means. However, in some other literature, for example, in TCS or theoretical CS literature, people often talk about the complexity of an algorithm, especially the implementational complexity. So like if I have the optimal computer, let's say a Turing machine, and if I have to implement the algorithm, what would its complexity be? And in algorithmic complexity theory based upon that, I'm getting too much into the weeds here, but basically the idea is you assume a prior, which is of this form, often called the universal prior, that if the complexity is high, I have a low prior. If the complexity is low, I have a high prior of implementing that behavior. So K of F is the complexity. Now, I don't have Turing machines lying around with me. So what I'm going to do is a fairly standard trick that people do in the literature. You write down Python files, you take a bunch of compression algorithms and run it through the compression algorithms, and just take the minimum value that you get out of that. So we're just going to gzip. And lo and behold, actually, lo and behold, in one more slide, what we're going to get out of this is essentially, under these assumptions, we're going to get an analytical expression for a free energy kind of term, which is the log posterior odds of a memorizing versus a generalizing predictor given some training data that the model observed. So you have the prior, the likelihood. We formed the prior being proportional to the complexity, the likelihood being proportional, having like a power law term, and doing a log of that gives you this expression over here, which is saying the posterior odds, the log posterior odds of implementing the memorizing predictor versus the generalizing predictor is dictated by a competition between two terms. The differences in their complexity, which solution is easier to express, easier to implement, versus the differences in their loss. If a solution has a better loss but is more complex to implement, I would prefer the simpler solution if it has close enough loss. But if the more complex solution has a really, really low loss, I'm happy with that, because in this trade-off, the delta L will become like a very small, will become a very large term, and it'll start to dictate the trade-off. So based upon this,
so are alpha, beta, and gamma free parameters?
Yep. Alpha, beta, and gamma free parameters. Technically, gamma has a closed form expression. Alpha and beta are the real free parameters here. Gamma is.
You can't measure alpha and beta from different experiments, or?
Yeah, so that's exactly what we're going to do. This is the log posterior odds, so I can turn this into a predictor by just running a sigmoid on this, and that'll give me this expression. The posterior probability of the memorizing predictor plus the posterior probability of the generalizing predictor times the predictor itself, and that gives us these results. So this is again like a closed form expression, where this is the plot I was showing you before, the phase diagram of a transformer, and this is the equation that we just wrote down. What you see is like there's a extremely close match. Like this phase boundary is extremely well captured between the experiments versus the theoretical model. There's two parameters, well, three parameters that we have to fit. So what we do is like we take a few of these variations between the time and diversity axes and just do fitting to them. This is a very generous fit. In actuality, we need barely any samples over here to like do the fitting, so it's like very sample efficient. And what this is saying at a high level is that just this extremely simple 3-parameter model in fact explains a highly complicated system, 2 to 4 to 1 layer neural networks, and like the transitions that they exhibit between different algorithms. Personally, I find that extremely exciting, that like you can actually simplify these models to such an extent and get a precise algorithmic explanation out, which is this equation over here for the specific behavior in context learning.
So K before is supposed to be the Solomon, like your approximation to the Solomon prior by like just using the pregnant. How is the model sampling? It's supposed to be very hard to sample from the Solomon, right?
The model, like what we're saying here is like we're making an assumption that when the model was written down, you or like when you initialize the model, like the entire training pipeline, the gradient descent that you'll run through, the training data and all of that combined has a prior, which is essentially the Solomon of prior. So the sampling is happening during the training process. You're going through solutions in the loss landscape and arriving at a specific solution. And again, this just keeps working, by the way. We've tried like basically every ablation that we could run, or I guess sensitivity study, model size, amount of context to train on, blah, blah, blah. And pretty much consistently, the model and the equation, like they keep on consistently checking out. Their behaviors are very similar.
So do you have different alphas and betas for different applications?
Not so much for different ablations, but very much so for different tasks. So for example, like you can run literally the same fit for if the data remains consistent, but like if you change the model size, like then the alpha and beta will change. And you actually see like fairly predictive trends for that too. So for example, if I recall correctly, the beta expression, it keeps on increasing. Increasing as a function of model size. So like you do not care about, it keeps on decreasing as a function of model size because you do not care about the complexity penalty as much. And I think like similar trend happens for the power law scaling as well. And maybe too much in the weeds again, but one of the things that we talked about before, the time to change between algorithms, the phase boundary, we can in fact like make very accurate predictions. Like before you even run an experiment, I can tell you what the amount of time will be when that transition occurs based on this equation. Okay, so at a high level, now taking a step back again, what we did here was we wrote down a very simple mathematical formulation for the behavior that the model is exhibiting of transitioning between different algorithms, where we say that like there's a prior that the model has over different algorithms. In this case, it's a simplicity prior. It prefers simpler solutions. And especially if the diversity of the data, there's like a lot of functions to memorize, then in that case, memorizing solutions will be penalized more and generalizing solutions will be preferred. Meanwhile, the data is better explained, as in the loss is lower for the memorizing predictor, and these two factors are competing with each other to eventually arrive for leading the model to like eventually arrive at one of these solutions. So precisely the point where the likelihood of these two solutions and the prior odds, like the model has like approximately similar prior over the two solutions, or the likelihood is similar, that's the point where like these phase boundaries emerge. So when, for example, like if you keep on going through training and you keep on seeing more and more evidence for one of the algorithms, that evidence starts to flood the prior such that you cross the boundary and arrive at a different solution. Okay, this is great, but where we started off, many-shot jailbreaking. So we want to explain many-shot jailbreaking, right? What we have right now is a Bayesian account of transitioning between different algorithms. I'm going to say that like actually, essentially, the same account will hold for a llama model taken off the shelf for many-shot jailbreaking. So what I'm going to do is I'm going to assume the algorithmic account, and one more assumption, which is that beliefs, as in like belief in a concept. So like if you want to talk about, let's say, violent or hateful speech, my belief or like my prior of talking in a violent or hateful manner is encoded in the representations in a linear fashion. So this is essentially the linear representation hypothesis again. I am personally like very much in line with like, representations are much more structured, but there are times where it's valid to make that assumption because in fact like concepts sometimes are linearly represented. So in this case, what we're going to say is if the representation linearly encodes concepts, so like Zi is a specific concept, then if I were to add, if I were to steer the model, if I add like some constant m times that direction di to like to the model representation, intervene on the representation that way, the log posterior odds of a hypothesis of a behavior will change under the intervention versus the non-intervention, the null, as approximately in a linear fashion with respect to the steering coefficient m. This trickles out of the linear representation hypothesis. In general, like not claiming this is true, but just when the linear representation hypothesis holds for some concepts, this will happen. And based upon this, what you can say is that like if I assume my algorithmic account and this linear encoding of prior beliefs, you'll get this precise formula for the amount of context as a function of the steering coefficient and vice versa, for when the transition happens in many-shot jailbreaking. And this is the actual experimental versus prediction. So like the predicted context value versus the actual context value, where it's a fairly decent trend that now I can predict before you take a llama model and try to make it, unsure why you would want to do that, make it more Machiavellian or psychopathic or narcissist. But let's say you wanted to do that, then in that case, I can tell you how much context would it be before the model starts to engage in that behavior. And this is good news for us, because this means that like I can preemptively, like if the user is trying to like engage in that behavior, I can write down like some policy which says, if you reach a critical amount of context, we should probably shut down this conversation.
Sir, could you say again one more time, what are the measurements you need to make in order to make the prediction of the transition to these bad behaviors?
Yeah, so we need like these 4 free parameters now: A, B, alpha, and gamma. And yeah, so A and so technically we don't need A and B in this case. Like we're trying to create a more general phase diagram. That's why. But A and B are related to the steering of the model behavior using representations. So what I'm going to do is I'm going to look at the posterior that the model associates with like answers corresponding to this behavior as a function of the steering strength, and fit a, assuming the linear representation hypothesis, you get a precise functional form for that, how that posterior should change. And that functional form gives you these two free parameters, A and B. So you fit that to the data, and that functional form is simply a sigmoid. So the fitting is very easy to do for a specific context value. And you can run the same thing again, where if I fix the steering coefficient and I run just the
So you have to look at the probability of certain words that are associated with Machiavellianism or psychopathy or narcissism.
You can do something simpler, which is like I ask a question where one answer is more Machiavellian versus the other answer is not, and I just like look at the posterior probability associated with the yes versus no, like engage versus not.
So you have to have some examples.
Yeah. You can do this for like a tiny bit of the data, and then like you can just stretch out the prediction to see like whether the prediction holds. So that's essentially what's happening. So yeah, where we started off, we wanted to get an algorithmic account of many-shot jailbreaking. We started with like first creating a toy task which captures that, the high-level phenomenology, get into a toy model which captures the behavior and in fact exhibits like much more richer structure than we expected. Create a precise account, an algorithmic account of that behavior, based upon which you take a step back now, go back to the predictive part, and try to explain the actual large-scale systems behavior. So model systems approach. And we're not the only ones doing work like this. There's like several other groups, and like even like our own work has explored like other threads as well on this paradigm. Again, at least personally, I like to take inspiration from like cognitive and neuro literature. Roger Shepard, who, if I recall correctly, was a prof here as well, had this really fun diagram in a paper in 1968, I think, or 61, I guess, yeah, on trying to understand how humans perform classification of different shape, size, color combinations. We actually use this paper as inspiration, and like this structure as inspiration, to come up with an analysis of emergent capabilities, so like how capabilities can suddenly emerge in neural networks as a function of scale. Here in this case, it was scaling the data. And similarly, some other work that inspired models of explaining how neural networks can learn new symbols, and so on. In fact, Surya's own work is also, in my opinion, falls under some of this umbrella. For example, Mason and Surya, Mason, a PhD student with Surya, had a recent paper on this analytical theory of creativity, how models generalize outer distribution and like create novel, diffusion models generalize outer distribution and create novel combinations. Not exactly similar to our theory, but like I would argue fits very well the umbrella of like what I was talking about before with the in-context learning series, the rational analysis perspective, because in this paper, these guys get into the idea that like you think about the base optimal solution, and then you take into account the computational constraints that we're talking about a CNN. And if you take that into account, you can get like a very precise functional equation such that your theory versus the actual model, they make essentially or in this case, I would argue exactly the same, produce exactly the same output, which is essentially what we did with the in-context learning series. And at a high level, I also want to emphasize that like such papers can have a lot of impact. These were more like phenomenon that already existed out there and we were trying to explain, but often the predictions, when they are relevant to, let's say, safety or policy behavior, if the predictions hold on scale, they can be impactful. For example, like a series of papers we did on understanding the limitations of fine-tuning based post-training protocols for safety. They actually eventually found their way to like recommendations to the White House for how fine-tuning can be a big problem even via APIs for trying to release models, and how safety needs to be, like adversarial attacks and like adversarial paradigms of safety need to be treated differently when fine-tuning access is allowed. And again, there's several other groups doing really cool work on this from this point of view. There's this group at Harvard, Fernanda Villegas and Martin Wartenberg's group, David Bao, who were looking a lot into world models in neural network representations. There's a bunch of cool work that Neil Nanda used to do, doesn't do anymore, on understanding arithmetic and grokking in model representations. And in fact, based upon this reverse engineering of a toy model, where they found like this toy model uses like a Fourier transform-based algorithm for performing addition, you see that like that was the inspiration behind doing an analysis of like actual language models and finding similar features and like similar descriptions of even like a large-scale language model. If we didn't have the hypothesis, if we didn't have the toy system, it would be extremely hard to do this. But just because we had that, we could get into this analysis. And as a quick drop, Eli Pavlik's group has like a bunch of really cool work on this broader approach of model systems. Strongly recommend reading their papers as well. So yeah, model systems approach, I would argue, has been like a key missing piece of the puzzle. And some high-level takeaways in conclusion here now. Like we started off with the idea of levels of analysis, that like there's different kinds of explanations that exist, computational, algorithmic, implementational, and different interpretability approaches are like trying to attack the problem of explaining systems via different routes. Causal abstraction tries to go top down, have a hypothesis, explain the implementation. Something like SAEs try to go bottom up, take the implementation, try to explain the behavior. And what we talked about is like essentially what I would call is a cognitive paradigm in the making, how CogSci started to come in and like take like a middle ground, or when I was pitching this to David Bao, he said a middle out approach, in case that rings a bell for anybody who's watched Silicon Valley. It's essentially like a middle out approach, which tries to say that like you can actually, like both these paradigms can benefit from each other, can benefit from like algorithm explanations. And then like maybe we start to get like a full puzzle sorted out over here. And to that end, I would argue model systems approach can be like one paradigm or like one way of attacking the cognitive or the algorithmic part of the levels of analysis. So yeah, thank you so much. Quickly want to highlight my collaborators as well, especially Daniel, who's sitting right there. He did a lot of grind work on the ICL series. So yeah, cool. Yeah.
So when you're looking at these phase diagrams, they all seem to have sort of some curve in number of in-context examples and like training time. And at a certain training time, you stop learning, you stop using the memorizing algorithm at all. Is that?
It's more like the opposite.
Okay.
Yeah, so as a function of training time, as you keep on going through the time, yeah, you start to do the memorizing one. And like, which makes sense, right? Like to start off, I don't know, like the precise solution which will get me the best loss is not necessarily something that's known to me. Like I don't know where in my high dimensional landscape it lies. But there's a lot of solutions which have like decent loss, but are simpler to fit, simpler to implement. So I can easily arrive at those solutions first. So that's kind of sort of what's happening over here.
So I guess the thing that's slightly different about this in your first example was like this is something both axes are about the training set, right? But in the in-context learning setting, the trained model seems to actually be like going over this phase boundary.
Yep.
Which means that like in some sense it has to have learned this function, this free energy, which is supposed to be telling you which algorithm to use and know both algorithms. But this model never knows both algorithms. Is that correct?
That's maybe like the strong version of the statement. I'd say like let me just try to paraphrase, or maybe also answer in the pursuit of paraphrasing, which is this analysis is currently for a fixed context. Depending on the task, the context is different. But here, if I recall correctly, there's like 128 context. And what's happening is you are simply trying to gauge what is the posterior probability associated with the two algorithms. You can analyze essentially produce the same Bayes diagrams as a function of context as well, right? And that's what we were doing here. So this is now, if you take a slice of this diagram, that's like that diagram that we just saw, and like the z-axis over here, technically the y-axis, but assume the protruding axis towards you, that's the context axis, and that's an inference time axis.
So that means that the model has to have all three of those algorithms learned and somehow stored in weights.
Yep. And like actually we give like descriptions of the implementation as well on like how that happens and how like even the trade-off happens between them, which is kind of commented upon in the other paper that I was mentioning, and then like in the final paper that we just saw, like explaining many-shot jailbreaking, that model is in fact what we use for explaining the many-shot jailbreaking results. So in that final paper, we're saying like we don't exactly know how the implementation works, but we're going to assume that the implementation is there. Here, as you were saying, like the implementation has to be there. That's how the model will trade off between the algorithms. But like the system is toy enough that I can actually provide you the implementation. So like I can literally take the MLP weights, for example, and I can recreate the transition matrices for the Markov chains. So yeah.
Hey, this is great. Can you reconcile the plot? I mean, I guess continuing to start a little bit, how more and more data, it kind of slowly shifts over into a memorizing solution. Double descent. How those reconcile?
I wouldn't quite put them in the same bucket right now. Double descent is a multi-epoch training phenomenon. This is an online learning setting we're in. So like we're not observing the same data point, or we're very unlikely to observe the same data point again. And in double descent, what's going to happen is that you have in fact like reached the global optima, as in like the loss is 0. You've perfectly fit the data. And then you're simply increasing, for example, the amount of number of parameters in the model. And you see that like, there's a critical point where like suddenly the loss will start to go up and then starts to come back down. But like the loss is the val loss will start to, like validation loss will start to go up and come down, but the training loss is constant. It's always 0. In this case, like this is essentially the training loss, because the validation and the training loss are the same, because we're talking about online learning. So I wouldn't put them in the same bucket. That being said, the phenomenon the high level picture of there's a prior that I have over different algorithms, and like as a function of training data, I'm like I'm updating my prior over different algorithms. I'm fairly certain like we can put double descent in a similar picture as well. Just the notion of the prior will be very different here, because I expect it'll be different here. Or maybe the evidence accumulation might be different. The prior will probably be the same, because here the evidence accumulation follows a power law. In multi-epoch training, eventually power laws break down, generally about 3 to 4 epochs. So I suspect like that's where the breakdown will occur. Yeah.
Great. I think we need to vacate for the next class, but we can hang out outside and chat more. So let's thank Ekdeep.
Yeah. Thank you so much.